Hello, everyone. So actually, for this episode of The Next Experiment, we're flipping things up a bit. So first of all, we're doing quite an unusual thing of recording live at the Jump Discovery Summit here in Sorrento. And secondly, usually we're talking all biology, and we're talking to biologists about the challenges that they have with biology and how they're trying to address these with high-powered experiments. But today, we have the great privilege of talking to a chemist. This is Dr. Lyndon Schrecker, who is the CEO and founder of Solve Chemistry. So this then flips it round between me and Phil, because usually I'm the one who has that somewhat comfortable position of being the domain expert and understanding what our guest is talking about, even when they get into quite a lot of technical detail. And Phil's the one who then, is like trying to explore his way through the subject. Yep. And it's very much flipped round the other way this time.
Yeah. So I'm looking forward to spending the next 20 minutes talking about Suzuki couplings, Diels-Alder reactions.
I'll try and keep it out of the weeds for you, Marcus. I think you'll keep it nice and light and statistical.
You're very gracious.
Yeah. So welcome, Lyndon. Thanks for joining us. This podcast is all about trying to get more people using smarter experimentation methodologies. We talk a lot about the problems with how people are doing traditional trial and error, one factor at a time experiments. And so I was wondering, was there a particular time when you realized that there was a need to do better experiments?
Yeah, so though I did my PhD in kind of automation chemistry and now run this kind of automation AI chemical company kind of thing, I actually started out as a traditional kind of what I always describe as a kind of hardcore, old-school organic chemist.
Right.
So really trying to extract molecules from trees, try and recreate them in the lab kind of thing. At Oxford for my undergrad in my fourth year, when I was first kind of actually in a real research lab, I fairly quickly realized that though I like the curly arrows, and sorry to get technical already, but the kind of the theory behind of organic chemistry a lot. The practicalities when it came to real research, there was a lot to be left desired there. So I remember the first experiment I actually did in the research lab was trying to replicate a paper that was published in a good journal. It was work from the University of Tehran, and it said, okay, do this, mix A and B at room temperature, leave overnight, and then you get a quantitative yield, so you get full conversion resistance. I was like, great, that'll be a nice, good start, get a nice fun on the chalkboard here, get something, get some work done on day one. Came back the next day after setting this up, no yield at all, really, very, very confused. I was like, reading things, I was like, I've done everything that it says here in this paper. It should be repeatable, right? That's what a paper's for. And I was like, University of Tehran at room temperature. Now, I'm in Oxford in the winter here. They don't really heat the labs in the winter at night for kind of very, very admirable sustainability reasons. Yep. But it does mean that chemistry didn't work at all. So left it the next night at 30 degrees, quantitative yield. So it shows that that really made me think that it's not enough to write down the things that you think were useful for doing the experiment this time for repeatability of these things. You need to include things that help everyone repeat this kind of thing in the future. And that kind of led me, that was a kind of less frustrating one because I solved it fairly quickly, but there was more frustration throughout my master's about the kind of repeatability and the kind of the culture I was seeing in a lot of organic chemistry as well of some people not wanting things necessarily to be repeatable. They wanted it to be kind of magic in their hands sometimes, which is nice for the individual in the first instance, but then for a culture of science and growing scientific discovery kind of becomes a bit of a pain a bit later. So I then went through to do my PhD at Imperial between chemistry, chemical engineering, and data science. I've always liked having about a 70% new learning rate, so this was a nice sharp learning curve into that space. I'm working on originally self-optimization problems and then automation of how we collect data from chemical reactions in the most efficient way possible, and therefore how we can best use that for different machine learning applications for process development and scale-up.
Great. Yeah, and that was with Professor Mimi He at Imperial, who's a good friend of JUMP.
Yes, yeah. And I had a lot of interaction with JUMP throughout my PhD there. with Ben Dedman as well, who was at the time running RAW, which is, for the uninitiated, a kind of reaction high throughput monitoring lab that came out of an initiative called Dial a Molecule. So people, Mimi and people in that space thinking about high throughput experimentation, how best to use that data for a long time as well. And I'm just part of that story going forwards.
Great.
So Lyndon, we've had a lot of discussions about how we view experimental design and cutting through the complexity of our various domains. And part of the real interest for me is learning from what you've experienced within chemistry and thinking about how we can apply maybe your learnings and maybe sort of part of the sort of chemist's mindset to biology. Because one thing I've always really admired about chemists is that they're not happy if they don't understand something. Right? Like I think as a biologist, we often are just like, oh, well, it's all so complex. So, there's only so much we can ever understand. We're never going to be able to get to the heart of it all.
Yeah.
So what's your take on the kind of differences in the complexity between the spaces and what we can do to try and address that complexity?
Well, I think there might be a bit of the grass is always greener kind of stuff going on here a bit, but maybe I'm too deep in it to see that it's necessarily easier. But to me, sometimes the ability of a chemist to think that something can be solved fully, which it often can be, and it sounds to me much less so in a biological context, is that people then have the hubris to assume they actually can solve that thing and that they don't necessarily need to collect much data for that. So more reliance on intuition sometimes because of that, and and it's perfectly understandable. It's kind of, if you think you can do it with intuition, why bother leaning towards more statistical and data-driven methods? But I think we are seeing a shift in this now where people are thinking more in that way. I think the kind of advent of various machine learning and AI methods have helped people think more about getting more data through. Yeah.
That's interesting. So that kind of move from, yes, I can intuit these curly arrows, I can work out where all the electrons are going, and I can just work it all out myself, to thinking, how do we actually build a systematic system which could actually work all these things out, from sort of a software perspective, i.e. some form of AI or ML. Then they're then thinking more about the data they need to gather.
I think there's also been interest in seeing how if you collect more quote-unquote weird data, so areas where you wouldn't intuitively collect data, as you would with statistical methods, that you can lead to more interesting discoveries as well. Right. So for example, if you're trying to understand how a new reaction you've just discovered, developed is working, you might have an idea of the pathway it's going to go down, but broadly in the back of your mind, you're kind of like, I'd like it to be quite a weird one. Wouldn't that be cool? I could get my name to a particularly weird reaction. I'd like it to be helpful and useful to people as well, but I'd also like it to be cool. And by collecting more data, you can kind of sniff out more cool things that might be going on. Because despite kind of chemistry being simpler than biology, if you look at it enough, you can find complex things. It's then important not to have the bias of going, oh, it has to be cool, and making sure you're trying simple things first as well in a modeling perspective, kind of Occam's razor kind of style here, finding the simplest, well-fitting model instead of just throwing complexity at it and therefore finding a solution in the end.
Yeah, wow. And so, all of these realizations obviously came together at some point, and you decided you were going to solve all of chemistry. Is that the mission of Solve Chemistry? Is that why you named it?
Yeah, pretty much. I mean, so it started out as a more toy project called Solving Solvents, which is why it's got the kind of solvy bit going on a few times.
Yeah.
But then we realized that, so during my PhD, we got I at the time, I guess, got a patent on how we screen solvents, so the liquids that reactions are performed in, how we screen the effects of these on chemical processes and how they affect outcomes.
Right.
Initially from a kind of sustainability and efficiency perspective. But then I realized, speaking to lots of people in kind of big pharma and big agrochemical companies and specialty chemical companies, that because I thought this was a unique way of collecting a new type of data, so therefore people definitely didn't have it. But what I didn't realize at the time is people didn't really have data on a lot of these other things as well in an accurate manner. So how temperature affects the reactions, they might have kind of 3 data points, but they're unlikely to have a full kind of understanding. And that's fine if it's a nice standard kind of Arrhenius effect, so a nice well-defined effect of temperature, but often it's not, and it's nice to capture that. So we could then broaden our scope of techniques to these other areas as well, using a technique, not to get too technical, Marcus, but called transient flow, which allows us essentially to, instead of drawing dots in a kind of design of experiments or a process chemical design space, allows us to draw lines through that kind of high-dimensional space instead in a kind of continuous manner. And this obviously affects how you start to design your experiments as well as how you start to treat the availability of this data.
That's really cool. Yeah, so you're drawing lines and presumably surfaces, and yeah, amazing. Sounds really compelling. So what's stopping people from doing better experiments, the kind of experiments that presumably you're doing at Solve Chemistry? I mean, this is a big question we're trying to answer with this podcast in biology in particular, but in chemistry, what's stopping us doing more of this?
Yeah, so as a general mindset thing, I think you often end up either in academia or industry with kind of structures against you to how you would progress, and that we're not kind of rewarded for collecting lots of data if it's not immediately clear what the purpose is with that data. So the kind of example I'll kind of throw out is kind of in academia, you're kind of rewarded for publishing papers.
Yeah.
The paper is based on the novelty of what's going on. The then 100 data points you should collect after that is not really the novelty part, it's the repeatability part. So why would someone, unless they're feeling really altruistic, actually collect that data with a grant instead of just trying to get another paper? So we're not incentivizing academics in the right way to collect meaningful amounts of data, even though I would argue that the purpose of kind of the academic literature in a whole is to make it easier to do the next bit of academic literature, and that requires good data collection. Similarly, in industry, I think you often run into the problem of time constraints and short timelines. So for example, in process chemistry, when it comes to you to kind of scale up this milligram of a drug that's come to you from the discovery stage, and now you need kind of a kilogram of it going into some phase of trial. They want that yesterday, really, because that's eating into their patent protection time. That's wasting money by that time. So you don't have time to collect loads of data around this to build a good landscape. You're trying to do it in as few data points as possible towards the goal now, not thinking about, well, I'm sure people are thinking about how the data will be used later, but you don't have the time or resource to apply to that because you're under the time pressure to get it out now.
Right. Amazing.
So if we're to kind of, we've been talking quite a lot about conceptual things, and, you're absolutely right that I think a lot of the culture that we have set up and the incentives we have set up in organizations isn't necessarily the most conducive for sort of the long-term robustness and of our understanding of given systems. But I'm kind of really interested in, if we're going to zoom right back in again into your personal experience, obviously, you've had this sort of shift over time and looking to do things in a much more substantive way, shall we say, and have founded a whole company to do this now. Was there any particular kind of experiment which really sort of shaped that thinking as you were going, beyond obviously those first issues of reproducibility, but really then kind of you learned something substantial from that? Then you thought, okay, yes, actually there is this way that we can go to this much more substantive way of experimenting and learning about the system.
Yeah, so I guess at the start of my PhD, I was focused on a reaction called the Knorr-Pyrazole synthesis, which is considered...
It's one of my favorites.
Thank you, I'm glad to hear it. Not used in stock cubes, not Knorr from that, just to be clear. Don't put these chemicals in your food. But used in the synthesis of different drugs and agrochemicals to create essentially this 5-membered ring structure that's very helpful. Generally considered a nice, simple mechanism. I was using it as a nice, simple example to add a load of other complexity to in what I was doing. I was trying to do, if you collect data on a simple system, can you then use that data to apply to a more complex system in a kind of transfer machine learning way? However, what it turned out with this system is when I actually started collecting meaningful data on it, and this is a reaction that's been published on tens, hundreds of times kind of thing in the literature, some with kind of kinetic mechanistic understanding, and all saying it was a very simple kind of linear scheme for this. And what I found from just a couple of experiments is that this was clearly a load of rubbish, and it was in fact much more complex and not a good example for what I was trying to do was the transfer learning at the time, but a very good example of if we design experiments to collect lots of meaningful data, we can really shed the light on the complexity of this mechanism. And this is where I really got into some of the transient flow stuff as well, is I realized in a normal kind of chemical system, you can collect data over time series very easily because you leave something running, time naturally progresses. Great, you've got a time series. But I realized the way to probe these kinetics best was to fix time, so have a fixed kind of cumulative flow rate in my system, and then vary the ratio of the A and B flow rates in the system. So therefore I could get essentially 50 experiments out of on different relative concentrations out of the same amount of volume and the same amount of time as doing one time experiment. And we knew the time series ones, so we wanted more detail on this other axis. And that one experiment could immediately in 20 minutes disprove all these previous hypotheses, which has really made me excited about developing new experimental methods and the value they could have from the efficiency from the experimenter's side, as well as the results you actually get out of this.
Wow.
Yeah, I don't know whether it's kind of a mixture of, I don't know, schadenfreude and arrogance, but I love it when a really well-designed experiment disproves a large swathe of the literature. and it happens a lot more than you'd think. Well, it kind of depends on your opinion of the literature, I guess, but it happens more than you'd think in terms of, and it's really satisfying, especially for a community such as ours, to know that actually these aren't just abstract concepts of, doing multiple factors all at once or whatever, but it actually, we can make progress where many others have really struggled over a long time. And yeah, okay, maybe that is a bit arrogant, but it's arrogance on behalf of the methodology and on behalf of these things that we've happened to come across in our careers.
I think something that comes into that as well, which I'd be interested to hear your guys' thoughts on as well, is how much can you trust? How should you think about trust of existing data sets as well, as opposed to you don't ever want to go, oh, no one knows anything in this space before, despite there being 50 years of academic research in it. You don't want to start from zero. We don't assume that if we heat something up more, it doesn't go faster, right?
Right.
But how much should you encode and how much flexibility you can have in that encoding in advance feels very important in order to maximize the value of the data you then collect on top of this.
Yeah. I mean, I've seen a lot of people who have this imperative to use all this historical data, and I think probably my advice over the years has generally been just forget about it. Just start collecting really good data now.
Yeah.
Forget about all that stuff in the past. But I don't know. I'm beginning to think I'm maybe wrong on that. There is value.
I think I've got a similar attitude, but it's more that instead of saying forget about all the historic data, it's that even if you have all the historic data, collecting more data now is a very valuable thing to be doing. Especially, I think people think of kind of AI models trained on large scientific data sets as replacing the need for new experimentation. And I actually think it makes it even more important to have automated and quick ways and useful ways of doing experimentation, because you want to be able to prove out the results of this. And we're going to have so many more hypotheses to test that therefore you need the data in order to test that.
Yeah.
So it becomes more important whether you're pre-training on the data or not. We need more data now, and it needs to be collected in the right way.
Yeah, I think that point about hypotheses is where I would most put previous work. Right? Like, actually, people have looked at all sorts of different things, and that's a great place to go when you're considering all the factors you might want to look at in an experiment. And these days, LLMs are exceptionally good at that, right? I think they, in our experience, relatively limited so far. They're not very good at generating experimental designs at all, because I kind of consider that as quite a defined problem where you have to have a very defined output, and I don't think LLMs tend to be very good at that. But what they are very good at is giving you a load of suggestions for factors you might want to look at, because they're looking back at all that literature, which we know the actual results might be dubious, but the ideas and the factors they've explored are not.
Right. Yeah.
And I think this is this is a very important point of kind of using the right tool for the right job within the process as well, not just slapping an LLM at everything and going, oh, solve the whole process.
Yeah.
Even with kind of self-driving cars, that's not what's going on. It's a combination of different models, some physical, some kind of AI for solving this problem as well. Yeah, I think that works well. And how we've seen our use of kind of LLM kind of parts in this space is that they work much better if you already have some data to give them a handrail to hold on to. If you just let them go with no kind of pre-training or no prior knowledge from your system, you're kind of keeping that from them in a way that's not valuable. And if you consider them, and I know we've spoken about kind of humanization of AI, but if you treat them as a kind of team member, you don't want to be combative with them, you want to be collaborative with them as well, right?
Right.
And therefore, why should you hold back data that helps them originally?
You don't want to be deliberately trying to trip them up, yeah?
Yeah. So maybe just before I get into the last question, I just wanted to give you an opportunity to plug some of the things that you've been doing recently with Solve Chemistry, and I know you've been doing something that integrates with JMP as well.
Sure, yeah. So we've just built so fundamentally as a company, we're, as you might expect from what I've been talking about, very good at collecting large amounts of data accurately, very quickly. That helps people make process development decisions in chemical process development and scale up much more efficiently, not just for now, but for the future as well, as we're collecting data that helps them change their mind on these decisions. So not just simple optimization, actually giving people the insights that allow them to make decisions on their own later as well. So printing kind of microkinetic models, solvent replacement models, things like this automatically. And yeah, really leaving the decision-making part with the customer who has a lot of that existing background knowledge that they're not necessarily going to share with us for these things as well. Into JMP, to make sure we're getting best use of this data as well, we've built a add-in that's on the add-in marketplace now, for porting data in and out of JMP as well in a standardized way, so that you don't need to download it from our database onto the computer and then upload it back into JMP. We want to make sure that softwares in the space really well handshake with each other. And I think that's the responsibility of the companies doing this rather than it is of the individual users as well. We should make it a nice, clean process for people doing this. People don't go to a shop and have to choose the appropriate packaging for their food. It comes as one thing already, right?
Yeah.
We want to make sure, I don't quite know if we're the food or the packaging there, but you know, you need to make sure that it flows through nicely into JMP, and we're looking forward to building more stuff around this as well. And it'd be great to see how people use this and how we can develop this further.
Amazing.
Tasty data.
Tasty, tasty data indeed.
Great. And so just one final question, and it's a very easy one, I think. What is the future of experimentation?
A very easy and very open question. So I think no matter how people feel about the different tools that are going to be used in the future, whether it's an AI-driven paradigm or kind of still has a lot more kind of human intuition going into it, still it's going to be very important to be collecting data in an accurate manner, and especially the metadata around this as well, to kind of bring it back to my original story there. Without metadata and context, there's only so much a human can do, there's only so much an AI agent can do with that. It's important not to just kind of rest on the laurels of the past of going like, oh, they collected data like this, so it's fine for me to collect data like that. We should be collecting data that's looking forward to the future, the kind of classic adage of a wise man plants an acorn for an oak tree that he will never sit under, right?
Yeah.
It's that kind of thing with data. We need to be really paying it forwards with the kind of data we collect and how we think about this.
Yeah, what a wonderful vision of the future of experimentation. Thanks very much, Lyndon.
Thanks very much. It's been great to be here. Thanks very much, everyone.
Thank you.